Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss design details of shell and tube heat exchangers. I will only be discussing details for an ordinary shell and tube exchanger, assuming liquids on both the shell and tube sides. Condensers and reboilers will be discussed separately. There are three sorts of exchangers that are in common use. 1. Pull-through or split-ring floating head. 2. U-tube bundle. 3. Fixed tube sheet, that is, both ends of the tube bundle are permanently fixed to each end of the shell. 1. Fixed tube sheet. The advantage of a fixed tube sheet exchanger is that it is a true countercurrent flow exchanger and no reduction of the log mean temperature difference, LMTD, is required for non-true countercurrent flow between the shell side fluid and the tube side fluid. However, it's impossible to mechanically clean the shell side, as the bundle cannot be extracted from the shell. When such an exchanger fouls on the tube side, it can easily be cleaned. When it fouls on the shell side, you can throw the entire exchanger away. 2. U-tube bundle. The tube side of a U-tube bundle can be cleaned, including the return bends. The problem is not tube side cleaning, but tube side inspecting. There is no practical way to see if the tubes have actually been hygroblasted clean. While a U-tube exchanger is less expensive than a conventional floating head exchanger, 10 to 15%, it should not be used if tube side fouling is a factor. 3. A floating head bundle is designated as an AET pull-through floating head exchanger or AES floating with a split ring backing device. This sort of a bundle has one fixed tube sheet and one floating tube sheet. One end is left free to float to accommodate the differential rate of thermal expansion between the shell side and the tube side. In this exchanger, the tubes are straight and can immediately be inspected to see if they have been properly cleaned. However, unlike the fixed tube sheet configuration, this floating head bundle is not a true countercurrent flow configuration. Hence, its LMTD must be reduced by the F-factor correction factor for non-true countercurrent flow. The floating head exchanger is quite a bit more expensive to purchase than the U-tube or fixed tube sheet exchangers. Also, your maintenance department will generally dislike making the gasket closure between the floating head cover and the floating head tube sheet. Finally, it's not uncommon for this closure to leak when the tube side pressure exceeds the shell side pressure. Still, the AES or AET exchanger is typically the correct design for almost all applications. Shell or tube side. The fluid with the high viscosity belongs on the shell side. The objective is to avoid laminar flow and high heat transfer film resistance. Typically, the higher viscosity fluid has the greater fouling tendency. Thus, the normal practice is to place the dirty, higher viscosity fluid on the tube side for ease of cleaning. However, if the shell side is designed correctly, it is quite straightforward to clean. I'll explain the design criteria for ease of shell side cleaning. But first I will explain the critical parameter called vortex shedding. Vortex shedding. When fluid flows at a 90 degrees angle across a tube, it creates turbulence, which is called vortex shedding. The swirls created when a river flows across a tree stump is a common example. The swirls destroy the film resistance to heat transfer created by laminar layers of fluid surrounding the tube. Experience indicates that a shell side crossflow velocity of 3 to 5 feet per second is sufficient to obtain this benefit. To calculate the crossflow area, determine the open area between the tubes at the edge of the tube support baffles. For example, baffle spacing equals 10 inches. Number of tubes at edge of the tube support baffle equals 20. Tubes are 1 inch on a 1.5 inch center, or half an inch space between each tube. Therefore, crossflow area equals 10 inches times 20 tubes times half an inch equals 100 square inches divided by 144 is equal to 0.70 square feet, neglecting gaps at end of tube rows. If the fluid flow was 3 cubic feet per second, then the crossflow velocity would be 3 divided by 0.70 is equal to 4.3 feet per second. This is approximate as I've not accurately accounted for gaps at either side of the row of tubes. There are vivid examples of the terrible consequences of placing high-viscosity industrial fuel oil on the tube side of a water-cooled exchanger. The second reason that shell-side flow is not subject to laminar flow is that the liquid only flows the diameter, several feet, of the shell, before its direction is reversed by the tube support baffles. That is not far enough to establish laminar flow. In the ordinary range of operations, there is no such thing as laminar flow on the shell side. Adjusting for cross-flow velocity. The designer ought to specify the baffle spacing to achieve the desired cross-flow velocity. In a 20 feet long bundle, a minimum of about 5 baffles are needed to actually support the tubes. The remaining baffles are to induce an adequate cross-flow velocity. Engineers have designed tube bundles for 30 baffles, that is, 8 inches spacing, with no problems. Just remember that doubling the number of baffles increases delta P by a factor of 8. Let me explain. 1. Delta P varies with velocity squared, which has doubled. 2. Now multiply by the flow path length. 3. 2 squared times 2 equals 8. I use a baffle cut of about 25 to 30%, but not for any particular reason. It's just that it seems to work out okay. Design the shell side for ease of cleaning. There are 2 ways to design the shell side of an exchanger for fouling service. Using 3/4 inch tubes on a 1 inch rotated square is okay, but not as easy to clean as the smarter method. Of course, being smart costs money. Meaning the smart tube bundle ID will be roughly 20% bigger than the stupid bundle. But that's a small price to pay for putting the higher viscosity fluid on the shell side rather than on the tube side, and then suffering from laminar flow. Tube materials. One excellent way of suppressing shell-side fouling, and tube-side fouling as well, is to maintain tube smoothness by retarding corrosion. Basically, use alloy tubes, 316 stainless steel if chlorides and caustic are not present, rather than carbon steel. Don't make the mistake of using carbon steel tube support baffles and 316 stainless steel tubes. A galvanic cell will be created that will destroy the carbon steel tube support baffles. I've seen the result of this error on an HDS unit reactor effluent. Don't rely on sacrificial anodes. They are not reliable and are typically not replaced in a timely manner. Construct the entire bundle out of 316 stainless steel. It's likely 2 to 3 times more costly than carbon steel, but the shell and installation costs, 90% of the total, will not change. And rates of fouling will be reduced, often quite dramatically. Tube side velocity. Constraints exchangers can be any even number of tube side passes that produce the desired tube side velocity. Depending on the tendency of the tube side fluid to foul, a minimum tube side velocity will be 3 to 5 feet per second. A maximum is 10 to 12 feet per second to avoid erosion, based on the nature of particulates in the feed. More importantly, remember to stay well above laminar flow, as defined by Reynolds' number, that is, above 2000. Reynolds' number equals tube ID times flow density divided by viscosity. High viscosity being the big factor. Also, delta P, as discussed above for the shell side flow varies with the number of passes, cubed, not squared. That is, flow path length doubles when going from 2 to 4 tube side passes. Meaning, if I convert a 2-pass exchanger to 4-pass, the fluid has to flow twice as fast and twice as far. Terminal tube velocity. The effects of excessively low tube side velocity will be to damage the tube bundle due to terminal tube velocity problems. When a tube in fouling service, where the colder fluid is on the tube side, begins to foul due to low tube velocities, the flow through the tube is reduced. The tube gets hotter, which further reduces the flow as it fouls quicker. The resulting suppressed velocity then accelerates the rate of tube side fouling until the tube plugs off entirely. Now the totally fouled tube heats up to the shell side temperature, while the tubes that are not plugged remain cooler. The resulting divergence in tube temperature causes the hotter tubes to bend and distort due to the differential rates of thermal expansion between the cold tubes, not plugged, and the hotter tubes, totally plugged. I see this frequently when tube bundles are extracted from the shell during a unit turnaround. The distorted tubes interfere with the proper fluid flow through the shell side of the exchanger and likely promote both shell side fouling and shell side bypassing. Also, as the tubes plug off, tube side delta P increases. If half the tubes plug, then the differential pressure across the channel head pass partition baffle will increase by a factor of 4 and may result in the failure of the channel head pass partition baffle. The designer should keep these factors in mind when selecting the number of tube side passes. Selecting too few passes and a low tube side delta P is often not a conservative design. Better to err at too high a tube velocity than too low a tube velocity. Exchanger nozzle sizing. Especially during retrofits, designers often neglect to check that revamped existing exchangers have adequate size nozzles. Tube side, the channel head nozzles need to be roughly as large in area as the cross-sectional area of the tube passes. Shell side, the shell inlet and outlet nozzles should be set roughly as large as the cross-flow area as defined above. This is conservative sizing. But I hate to waste valuable delta P on parasitic pressure losses across nozzles. Also, if the piping sizing is larger than my calculated nozzle sizes, I'll match up with the piping. If the piping is smaller than my calculated exchanger nozzle sizes, then I'll retain my larger exchanger nozzle sizes. Impingement plates and seal strips. The shell side impingement plate must be a bit larger than the inlet nozzle to protect the upper rows of tubes from the erosive action of the shell side inlet fluid. To accommodate the impingement plate, several rows of tubes must be omitted along the top of the bundle. The space so created allows the shell side flow to bypass the entire tube bundle by sneaking across the top of the bundle. To dam off this bypass area, a pair of seal strips is needed. These are typically a 1/4 inch thick, as long as the tubes, and perhaps 3 or 4 inches wide. They are set in grooves cut in the tube support baffles on either side of the impingement plate shown in picture. However, when I said that the seal strips needed to be as long as the tubes, that is not quite right. One of the pairs of seal strips must have one strip that stops at the first tube support baffle. If not, the shell side feed would be trapped above the impingement plate. If we have vertically cut the tube support baffles, then the seal strip that is aligned with the edge of the first shell side tube support baffle should extend to the tube sheet. Normal design practice is to end both seal strips at the first tube support baffle. This is wrong design practice. It allows the shell side flow to bypass the exchanger area between the tube sheet and the first tube support baffle. To avoid this problem, the seal strip at the edge of the first tube support baffle must be extended to the tube sheet shown in picture. Backflush connections in water coolers. I prefer to place water cooler backflush connections on the channel head cover. This is mainly because the piping design is not under my control, and thus the tube side backflush connection may be omitted by the mechanical designer. My rule of thumb is that I don't want the backflush connection to be less than half the ID of the cooling water supply line. You need to give backflushing a little extra thought if the exchanger is to be located well above grade. Will the cooling water return header pressure be great enough to backflush the tubes? For example, if the cooling water supply pressure at grade is 30 psig, and the exchanger is 70 feet above grade, then the water return header pressure will be under a vacuum and cannot be used for backflushing. Obviously, there is no neat answer to this limitation. Use of plant firewater is not advisable, because one should never divert firewater for safety reasons. Helical baffles. There are a number of novel heat exchanger designs that I am familiar with. Twisted tube. Tube inserts. Online circulating balls for tube side cleaning. Helical baffles. Spiral heat exchangers. The only one of the above that is in widespread use, and used with success in the correct application, is the helical baffle exchanger shown in picture. The tube support baffles are set at an angle to induce a helical flow pattern on the shell side. The idea is to avoid the dead zones that occur in a conventional vertical tube support baffle. Thus, delta P and fouling are both reduced on the shell side. However, I have 3 reservations. 1. If the controlling resistance to heat transfer is on the tube side, the helical baffle arrangement serves very little purpose. 2. For a new installation, it's likely cheaper just to buy a somewhat larger, conventional bundle than a proprietary helical baffle bundle. 3. The design angle of the baffles is quite critical to obtain the full benefit of the helical baffle bundle. The helical baffle bundle is best used during retrofits to existing exchangers, if the controlling resistance to heat transfer is on the shell side. Spiral heat exchangers are excellent in fouling services. However, after cleaning, they are difficult to reassemble without internal leakage. Correction factor for non-true countercurrent flow. When we calculate the LMTD in a heat exchanger, we assume the true countercurrent flow exists between the shell side and the tube side. For an ordinary exchanger, as shown in picture, this is not true. As a consequence of the channel head tube side inlet and outlet being located on the same end of the exchanger, the lower half of the shell is in co-current flow. Depending on the temperature profile, this typically reduces the LMTD by 5 to 25%. To calculate this loss in heat transfer efficiency due to this problem, we use the F-factor correction factor as presented in your TEMA data book. If you are unwilling to incur the penalty of loss of heat transfer LMTD as calculated by the F-factor, then you have 3 choices. 1. Place 2 exchangers in series on both the shell and tube sides. In general, this is the preferred solution and the one I would adopt. 2. Use double pipe exchangers. These are indeed true countercurrent flow exchangers, also called hairpins. I often use these. They are reliable and robust, but if the required capacity exceeds several hundred square feet, they are too small for many applications. 3. Use 2-pass shell exchangers. 2-pass shell exchangers. This picture shows that such an exchanger is in true countercurrent flow. The shell side inlet and outlet nozzles are located on the same side, close to the channel head. The cross baffle shown, longitudinal, is required to direct the shell side flow along the length of the shell. This looks good on paper. But the problem arises in sealing the cross baffle to the interior of the shell. This is accomplished by means of seal strips. I'm using the term sealing strips in a completely separate way than used in the preceding section of this video. The seal strips, as used in association with the longitudinal cross baffle, are very thin, flexible strips of metal clamped to both long sides of the baffle, as shown in these pictures. There are 2 problems with these strips. First, they are subject to corrosion unless the proper material has been selected. Second, they must be replaced each time the bundle is pulled. If these conditions are not met, then the shell side liquid will partially bypass the majority of the tube surface area, and heat transfer rates will suffer. I have seen new exchangers of 2-pass shell configurations work well when new. However, with time and typically after a turnaround, performance has been degraded due to leakage around the crossflow, longitudinal baffle. American Oil prohibited their use because of this problem. I also adhere to this practice and thus will select placing 2 exchangers in series, which is the more expensive option, as opposed to relying on the 2-pass shell alternate design. For most applications, 316 stainless steel is used for seal strips as flexibility and corrosion resistance are required. In non-corrosive services, copper alloy seal strips are used. Selection of fouling factors. I see a lot of variation in the industry as to how designers specify exchanger fouling factors. As a conservative designer, I tend to use larger fouling factors than most. Much better to add in a safety factor this way than to assume larger than anticipated flows. If the flow is much less than the design, the velocities will also be too low. A big fouling factor is typically 0.010 to 0.020 inch/hour, square feet, degree F, divided by BTU. For example, I might use 0.025 for extract from tar sands, a really nasty service or vis breaker fractionator bottoms or resid from a deep cut vacuum tower. For clean, light crude oil downstream of the desalter, I would use 0.003. For heavy crude upstream of the desalter, I would use 0.007 to 0.010. For jet or diesel, I would use 0.002 to 0.004. For heavy gas oil, about 0.005. For light hydrocarbon reboilers, about 0.003 would be okay for virgin services and 0.005 for thermally degraded products that have not been exposed to air. If you have a thermally degraded naphtha that has been exposed to air, then 0.010 to 0.020 would be a reasonable fouling factor. The steam side of exchangers is not subject to fouling. Yet I would still use 0.001, just to be conservative. For air coolers, I would also use an airside fouling factor of 0.001. What is far more important on an air cooler is the tube side fouling factor. The external finned area of an air cooler is typically 20 times larger than the tube internal area. Thus, if a tube side fouling factor of 0.002 is used, it must be multiplied by 20 to obtain the effective fouling factor, based on the air cooler finned area. If the overall heat transfer coefficient for the air cooler is 10 BTU per hour per square feet per degree F, then the 0.002 tube side fouling factor will represent 24% of the total heat transfer resistance. Step 1, 0.002 times 12 is equal to 0.024, where 12 is the ratio of internal area to external finned area. Step 2, the reciprocal of the heat transfer coefficient, 10, is the sum of the individual heat transfer resistance 5, that is, 1 divided by 10 is equal to 0.10. Step 3, 0.024 divided by 0.10 equals 24%. For ordinary tubes, I never bother about the small effect of the ratio of outside area divided by inside area. But for finned, studded, or serrated tubes, that is, low fins, this ratio of area factor is really important, as it magnifies the effect on the tube side fouling factor that is selected. Selection of allowable DP. This is a complex and difficult subject. The larger the specified design increment P, the more latitude the exchanger designer has to configure the exchanger for high velocities and a lower Reynolds number. If we specify too low an increment P, then we force the exchanger designer to specify low velocities. If we specify too high an increment P, then the designer may not choose to consume the available increment P, which is then wasted across a control valve. So, I guess my approach is best. Specify yourself. Size, length, and number of tubes. Tube ID and pitch. Number of tube passes. Baffle spacing on shell side. Baffle cut, then, you will get the exchangers you really want every time. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.